All right, we're back for solubility. So this one you're going to definitely get your calculators out because you got a bunch of exponents. The solubility of barium sulfate is 9.09 times 10 to the negative 4 grams per 100 mil of solution at a particular temperature. Find the KSP. Okay, this is a tricky question to answer, but we've got a lot of stuff going on. We've got milliliters and grams, and we also have a conversion here. We have barium sulfate. Okay, so I'm gonna need some details here. I'm gonna definitely need my periodic table because I need molarities for this kind of thing. And so I need to get my barium sulfate on here. All right, I might regret doing this one off the cuff without preparing. So barium sulfate, barium SO4, right? So that means that I have 137.33 grams per mole. I've got a sulfate, which means it's got sulfur, which is 32.07 grams per mole. And I've got oxygen, and I've got 4 of them, so I've got 4 times 16.00 grams per mole. So in total, I've got to get my calculator out. 137.33 plus 32.07 plus 4 times 16. With all the higher level concepts in this course, it almost feels backwards to be going back to calculating out molar masses. But that is kind of the thing about chemistry, is it just keeps building and building and building. All right, so if we have 9.09 times 10 to the negative 4 grams of barium sulfate dissolving, then how many moles is that? So we have to multiply that, or we actually have to divide that, sorry. We're going to divide that by our molar mass, 233.4 grams per mole. Or I suppose many of you took this class with Michelle, and so she would have probably set it up this way, by multiplying by 1 mole is 233.4 grams, so you can do it by the mole ratio. I always just do it by division, but that's just how I learned how to do it. I'm going to use my E here, minus 4, and then I'm going to divide by 233.4. So I get something like that. So I've got 3.89 times 10 to the negative 6, and these are moles. Okay. Now I need it to be in moles per liter, so I'm going to take 3.89 times 10 to the negative 6 moles divided by 0.1 liters, since it's 100 milliliters. This gives me, take that answer and divide that by 0.1. I could have guessed, I guess, 3.89 times 10 to the negative 5 moles per liter, or molarity. And are we done yet? Oh no, of course not. Whoa. Okay. Get back there. Go out of the way. Remember that we're still trying to find KSP. So the KSP in this case is equal to the amount of barium, 2 plus, times the amount of sulfate in the solution, 2 minus. And so from this it's a 1-to-1, so we can think that this is barium sulfate, SO4, going to solid, and Ba2 plus SO4, 2 minus. I almost feel like I don't quite remember doing these questions as much, but possibly because we had our student teacher teaching us at this time. So yes, that sounds right. So so taking this equation, we can see it's a 1-to-1 ratio. So as much of this, if this is the amount of barium sulfate, then it's also equal to the amount of barium, concentration of barium, and it's also equal to the amount of SO4 2 minus. So we're going to actually be replacing both of these numbers with this 3.89 times 10 to the negative 5, 3.89 times 10 to the negative 5, or taking the square of this value. So we can take this answer, we can put some brackets on it. This is what I like about a good two-line calculator. Will let you really get in there. And your final value is going to be 1.52 times 10 to the negative 9. All right, that's a pretty challenging question. Do I like it? I'm not sure. I'll think about it. The solubility product of Ag2CO3 is this. So that's the solubility product constant. This is KQ, or KSP here. Calculate the molar solubility. So this is the reverse of the previous question. Is that really worth all this effort? Well, I don't know. Yeah, I think I like this question better than the previous one, if anything. So here we have to take into account that this is solid, and it is undergoing an equilibrium where you have Ag ions, 2 of them, aqueous, plus CO3, 2 minus, aqueous. And one of the tricks about this is however much you can dissolve in solution, it will be equivalent to this sort of idea. So initially you'll start with some amount. It'll be 0 to start, right? And the change will be plus 2x and x and plus x. So our equilibrium values will be 2x and x, which means that if we set up our KSP, which is the silver, times the CO3 2 minus, I'm like thinking about how I imagine these video series would be very short, but I guess a 3-hour exam is a 3-hour exam, right? And we have to remember that this is squared because of the coefficient on the silver. And then we replace it with the 2x and the x. So now we have a little tiny equation here that we'll have to solve for. So the setup for this type of equation, and this actually will apply to anything that is set up this way with one ion that has 2 and the other ion that doesn't, is we'll have 4x to the power of 3. There's a little bit of exponent addition happening there because of the exponent rule, and then I also did my 2 to the power of 2 there. So now I simply take my KSP, which they gave me, 8.3 times 10 to the negative 12. I'm going to set that equal to 4x to the power of 3. I'm going to do some shenanigans here, divide by 4 to get rid of the 4. I'm going to take a cube root of the whole thing to get rid of my cube and see what happens. So let's get this all set up. I've got a cube root of 8.3 e. This is why I really encourage you early in the year to figure out how to use those e functions on your calculators. Really key. Or your multiplier function, whatever you have, really key to being able to use your calculator effectively. Wow, I really wished my calculator would pump this out with the proper notation, but that's okay, I can do it myself. 1.28, it looks like, 1.28 times 10 to the negative 4, and that would be molarity. It's not fun. Okay, well, I really like these questions, honestly, but it is a little bit tricky. Show the calculations that would explain if a precipitate is formed when this amount of sodium chloride is added to this amount of silver nitrate. This is the common ion effect. I don't remember how much we did this, but let's see if we can do a little bit of calculation here and figure it out. So the trick is simply to consider the solubility of silver nitrate, which will be on your KSP table. So let's go find our KSP table. do I not have? I got common ions, negative ions. I got electrovolts there. There's my KSP. Oh, that's acids. Oh, we don't have a KSB table. Okay, so if I don't have a KSB table, then I really can't do much with this without looking up the KSP separately. So possibly this is just not going to be the kind of question we can do. KSP of silver chloride. Solubility problem. So if I gave you this question on an exam, I would have to give you the value. And it doesn't look like this is not what I was hoping for. What is a KSP? Here it goes. Okay. All right, so I would give you the value on our own. I think in this exam I had given all of my students a table of KSP, so that's why I don't include the number here. So here the KSP is equal to 1.7 times 10 to the negative 10. And we're talking about a KSP is equal to silver times chlorine minus. So we really need to just figure out how much chlorine we have, how much silver we have. So is a precipitate formed when 20, and I've always got to do it this way. I just kind of think about it as 2 jars. I've got 20 mils of 0.0010 molarity and 20 mils of 0.00010 molar, and they are now getting added together into one jar, and so this jar is going to have 40 mils, right? And so I need to know my two concentrations. So in this 40 mils, what is my concentration of chlorine from this? And this is my chlorine here, and this is my silver over here. Okay, what's my concentration of silver? So you can use the CV equals CV formula, C11 equals C22. This is the easiest way to do this conversion. And so we would say that there are 20 mils of chlorine times 0.0010 molar. And that will have a final, in the final solution, there are 40 mils times the new concentration. So we have to do a little bit of work here. 20 times 0.001 divided by 40. Okay, so my new concentration is going to be 0.0005 molar. That's my chlorine ion solution. Okay, I'm going to just switch pens to make it a little bit more obvious what I'm going to do in the next one. Here again, I have 20 mils times 0.12310 molar. And it's going up to 40 mils times concentration number 2. So 20 times 0.1231 divided by 40 gives me my concentration is 5 times 10 to the negative 5 molar silver. Okay, so now I calculate I do a Q test essentially of the silver, 5 times 10 to the negative 5 times the 0.0005 molar chlorides, and the result is 2.5 times 10 to the negative 8 is Q. Is Q bigger than KSP? So Q is certainly bigger than KSP. This is bigger than KSP, which is the value I didn't give you on this page, but I would have to give you on the test, the exam. And so that means that precipitate forms. Okay, let's take a break and come back for acid.